everyone. Welcome to this week's Crown Seminar. Our first talk is given by Guangtao Zhang from University of Macau. Yes?
Could you start recording, please?
Yeah, already started. I already clicked the recording button. And Guangtao is a second-year PhD student, and his research interests are physics-informed neural networks, PINs, neural operators, and automatic machine learning. He's going to talk about a new variant of PINs today called DASA-PINNs. So without further ado, welcome Guangtao. You may want to start your presentation.
Okay, thank you. Thank you very much. Hello, everyone. My name is Guangtao Zhang. Thanks very much for the invitation. I'm very honored to have this opportunity to present our work here. Today's presentation is about differentiable adversarial physics-informed neural networks. We develop a weighting scheme for pins. We name it DASA-PINNs. This is the outline of our presentation. We will first give the background and motivation of our project. Then we will introduce the architecture of DASA-PINNs. Next, we will show the numerical result of DASA in solving different PDEs, including time-independent and time-dependent ones. More specifically, we will show the results of solving Poisson's Helmholtz and steady-state least-driven cavity, Alenkine, advention diffusion, and diffusion reaction and wave. We also look at the performance of DASA on irregular domains, a solution with discontinuities. We consider both forward and inverse problems. For each PDE, we compare the result of DASA with the result of other versions of pins, i.e., cell-adaptive pins, HPV pins, V pins, G pins, weighting schemes based on NTK theory. Pins integrate PDEs and data into a loss to find the solution of the PDEs. Pins can learn relatively simple PDEs but fails to learn complex physical phenomena, especially for problems with stiffness and discontinuity. The possible failure modes of pins are not due to the lack of expressivity of pins, but it is because adding PDEs as soft regularization made the problem ill-conditioned. There are a few solutions in the literature, resampling and domain decomposition and adaptive adjusting loss weights. Resampling can lead to overfitting phenomenon. We will show examples when resampling and NTK fails in the next slide. By the way, our work is along the third line. We will develop a weighting scheme for pins. We use an example for illustration. This is a two-phase flow model. This example has three residual loss terms. If we resample the training points from a dense set, there will be a cluster of points in the physical domain. This will lead to overfitting phenomenon. NTK theory may not work sometimes. Our work focuses on adaptively adjusting the pointwise loss weights. We want to dynamically optimize the pointwise loss weights.
Sorry, Guangtao. This is Lulu from UPenn. Could you explain more why the NTK theory doesn't work?
Sorry, we just test. We use NTK theory to adjust the weights of different loss terms, but it showed that NTK theory doesn't work in the Alenkine equation here. Yes.
So basically, you mean the weighting based on the NTK theory doesn't work, not the theory doesn't work.
Yes.
Okay, I get it. Thank you.
Okay, thank you. Our work focuses on adaptively adjusting the pointwise loss weights, and as we mentioned about, we also want to achieve the goal of fair training on the whole computational domain. And we want it work for most of the PDEs, both forward and inverse problems, and we hope it easy to implement just a few extra lines of coding. Meanwhile, we hope it do not need a sequence-to-sequence learning, time matching, domain decomposition, but can predict the entire space-time at once. And this is the architecture of DASA-PINs. We have two networks, the backbone network and the subnetwork. A backbone net outputs the solution of the PDEs. The subnet outputs the loss weights for each residual point, and we multiply them together to get a modified residual loss. On the left is the modified loss for DASA-PINs. It's a bi-level optimization. We train DASA-PINs in 4 stages. In the first stage, we train the backbone network by gradient descent. And in the second stage, we train the subnet by gradient ascent. In the third stage, we adversarially update the parameters for 2 networks at the same time by the gradient descent and gradient ascent method. And finally, we will fine-tune the parameters of backbone network by gradient descent. And here are the details of 4 stages. The first stage, which only train backbone net with 5,000 iterations, and gradient descent is used. And in second stage, we train subnet 2,000 iterations, and gradient ascent is used. In the third stage, the most important stage, we adversarially train both backbone and subnet 10,000 iterations. Last stage, we train backbone only to fine-tune the results. We use 10,000 iterations ADAM and 2,000 iterations LBFGS. Gradient descent is used. And this stage, the weights for each training point is 1. Yes, I show here. And this is a bi-level optimization problem. We solve it by a simple approximation scheme. And this is what we call my method differentiable. We approximate the gradient of the subnet as follows. It is very easy to combine DASA with other versions of pins. For example, we can use Fourier MP in DASA. We test our method by solving various PDEs, including time-independent convex geometry solution with discontinuities. We look at single equation and couple equations. Both forward and inverse problems are considered. We first look at time-independent PDEs, including Poisson, Helmholtz, steady-state Lee-Driven cavity at different Reynolds numbers. We first test the one-dimensional Poisson equation. We consider 2 cases. One is the solution with a boundary layer, and the second is the solution with sameness in the middle, which are easy to solve. Which are not easy to solve using base pins. We use the modified 128 per layer, and we also use Fourier embedding here. As for the subnet, the architecture is the same as we mentioned about. We train the DASA-PIN with 2,000 points in the physical domain. Then we compare our results with HPV pins. HPV pins use variational form of the PDEs in the loss function. The error of DASA is 1/10 of HPV pins or V pins, even HPV pins using subdomains here. And then we test a 2-dimensional Poisson equation. We compare
Guangtao,
yes,
slow down.
hello.
Yeah.
Yes.
Why you get better results? Why your results are better? In the 1D case, let's go back to the 1D case. Let's say the 1D one-dimensional case where you have yes. On the right, when you have this jump in the middle of the domain. Why do you get better results? What makes it?
Okay.
What makes
yes,
your method better? What you have 4 steps. Which step was crucial and why?
Oh, okay. This is a good question, Professor George. I think the third stage is the essential stage because we adversarially train the backbone network and the subnetwork. Here, the attention, or in other words, attention is raised in the area that's difficult to learn. Yes. and because in other stages is as the same as base pins.
Do you have evidence of that, or I mean, how do you document that that step 3, the adversarial training, is important? How would you? Is it your intuition, or is it actually you can document it more rigorously?
Sorry, you means the third stage is
Why you're saying that the third stage is important? How do you know that that's important for this?
okay,
Oh.
yes, we do 2 experiments. Yes, yeah. The third stage, if we doesn't use if we don't use the adversarial training, the result will become it couldn't perform better than DASA-PINs. Yes, so it's the essential stage. And in the first 2 stages, we use to as pre-train stages, because we can train the backbone network and server network to better stage. Yes, okay.
Sorry, I missed something. So in my understanding, that the third stage is the first stage plus the second one, right? Because at the research training is you train these 2 iteratively.
We just use the adversarial training in the third stage.
Guangtao is a good time to go back to, because you have all stages in one slide. Maybe we can look at them a little more carefully.
Yes, okay.
So can you explain what specific have been done in the third stage?
Okay, in this stage, we use server network to output weights for each residual point, and we use the backbone network to output the solution, and we multiply the residual with the weights with the weights for each residual point, and we get a modified loss. And then we trained the server network by gradient ascent, and at the same time, after in each iterations, we train the server network using gradient ascent for using with 1 iteration, and we train the backbone network with a gradient descent with in 1 iteration. Yes, is adversary training. Yes.
Okay, I see. Basically, you fix one network, train another, then fix another one, train another one. So basically, stage 1 plus stage 2, right? It's some kind of right, because stage 3 is stage 1 plus stage 2, right? You do this many times.
No, it's a different rule. Actually, the first stage and the second stage are pre-training stage. And then during first stage and the second stage, he only use 1,000 or 2,000 for pre-training. The iteration are very, very few. But in the third stage, he use about 10,000 and 20,000 iterations here. So stage 3 is the essential stage here. And he use adversarial training here. So that's a difference.
Xiaoning, hi, by the way. Isn't like solving a minimax problem the same way that in the paper of Levi and Ulysses and Negro Braga from Texas A&M, they're doing it, just doing differently with a double loop.
Jordan, you meant self-adaptive pin, right?
Self-adaptive, yeah, the self-adaptive weight, yeah.
Right, right.
I think it's a similar thing that we are doing in self-adaptive.
I think Guangtao, you knew that self-adaptive pin, right?
Yes, I know.
It's common.
Yes.
Yeah, I see the SA pin is set in your abstract. So could you explain in stage 3 what is difference between adversarial training and the self-adaptive pin?
Okay.
So I think you have the same problem. You have the same min-max problem here in the stage 3.
Except they're doing with the adversarial. Yeah.
Right.
Yes.
Right.
Yes. Okay.
But
The main difference.
it's an ascent. It's a descent and an ascent, like they're doing. Yeah.
Right.
Yes, the main difference, I think, we apply the we want to use the output of subnet as the weights directly. We will use a scale operation, and the scale of the lambda will between the interval 0 and 1, and this will have a benefit because the range is stable. Yes, the range is stable, and compared to the cell-adaptive pins, they are made the updating rules of the weights. It may become very large or become very small between two iterations. And another thing is we use a subnet. Yes, a subnet has a general relativity. Yes, we for example, a residual point that the subnet haven't seen, and you can also maybe predict the suitable weight for it according to the point around it, and this is the advantage. And we also carefully design the architecture. Yes, the training scheme. We adversarially training. We have the pre-train. We have the pre-train stages, and we also have the fine-tune stages. And I just say that the third stage is very important, and we also has the benefit from the before two stages. Yes.
Hi, this is Michael from Utah. I just wanted, maybe I'm just misunderstanding adversarial, but I mean, I generally know it in the form of the general adversarial networks, and I just don't see solving this minimax problem. What is specifically adversarial about this? I mean, maybe I'm just missing something.
Okay, the adversarial training, we use approximation scheme for the subnetwork parameters. We the gradient, and we use a gradient percent, but it totally is as the same as cell-adaptive pins, but however we use the subnet, and it has an advantage. And meanwhile, I would just say that just now, in the network, the subnetwork has the generality. Yes. We can discuss more detail after the meeting. Yes. Okay.
Okay. Thanks.
Excuse me. Hi, this is Panos Tinis from Pacific Northwest National Lab. I think that the adversarial means that there are two networks playing one against the other, that the subnetwork is trying to increase the loss function, while the backbone network is trying to decrease the loss function. That's the adversarial part. And for the other difference with the self-adaptive weights is that here you're actually training a network to output the weights, while in the original paper, the weights are just evaluated at the different data points. So there was no network, I think, there.
Yes, Professor. The self-adaptive pins did not have another additional network.
Yeah.
Here, there's one network that's included.
Yeah.
But Guangtao, I'm Somdata from Brown. I just wanted to ask one thing. Since you added one more network, you actually increased a lot more number of parameters, which you have to tune again, because your subnetwork needs to be initialized, and you have more parameters to tune those to run into more problems. So how did you design this? Like, how did you design and affect the efficient network for subnetwork? You mentioned that you found out some way for doing that.
Sorry, you means the initialization way of the subnetwork and the architecture of subnet?
Yes,
Okay.
because when we were doing it with self-adaptive pins, we just have parameters within one neural network.
Okay, we just define subnet here. The subnetwork used here is just a fully connected neural network with a depth of 5 and width of 10, and we initial the parameters directly, and we fine tune its parameters in the second stage. As we shown here, we just update the parameters by using gradient ascent. Yes.
Okay. Thank you.
Okay, thank you.
Yeah, it's Kamal from Brown. Actually, I was trying to figure out actually in the self-adaptive weights the timing. So I like it should be 100% timing the total time. The self-adaptive takes only the 5% of the timing. So like the same thing, Somnath has commented, maybe the subnet will take more time.
Sorry.
Like if it is only the self-adaptive weights are there. So when I was working, so it's take only 5% of the timing, the total time. So if it is a properly network, then there is a back propagation, so it may take more time.
Yes, Kamal. I think you're right. Because Guangtao, Kamal said that in the self-adaptive payments, the lambda, they are unknown constants. So it takes less time to update them.
This time.
But
yes.
now you have a neural network, so it takes longer time to update in the gradient ascent. So that's right, Kamal?
Yes. Okay.
Yes.
Due to the network architecture of the subnet is a very small network, and our computational cost will less than the original pins because the updating rules directly depends on the number of parameters. Yes, I see.
Sorry to ask another question, but this is now from Sandia. Is there any interpretability? So for the subnetwork, do you have a sense of how it's deciding to choose those weights? So for example, if there's a gradient near the boundary, is it making the boundary term weighted more heavily or something like that? Do you have a sense of what's happening and what governs the weighting?
We haven't tested a similar result, but I will test after a meeting. Okay.
Mm-hmm. Okay, thank you.
Okay. Okay. Okay, and I will continue. Sorry. We could look at the Poisson's equation and Poisson's equation. Yes, we compare the result of with the G-pins, and here G-pins use hard constraints for boundary conditions, and even so, they cannot learn the interior where this is a peak of a solution in the center. G-pins has large error there. We also want to point out error of DASA is mainly near the boundaries, not in the interior. Error of G-pins is in the center. This demonstrates that DASA doesn't mitigate the gradient pathology among interior points. It learns solution in the interior better. DASA does not increase any computational cost compared with G-pins, but G-pins is most twice the computational time compared with pins. This is because calculating derivatives is time consuming for neural networks. We test another Poisson equation with in 2 dimension with a step-Z solution. We compare all the results with the HPV pins. The error of DASA is one hundredth of the HPV pins, and HPV pins use 16 subdomains. We also want to emphasize here that DASA learns the solution in the interior better, even for interfaces. Error is mainly near the boundary.
Hi, sorry, this is Michael from Utah again. So what is the comparison with this, just the self-adaptive pins? Because I mean, just comparing to HPV pins or the standard pins, I mean, what about other because there's other self-adaptive weights and weighting schemes. Where are those comparisons? How does it perform?
We haven't tested other self-adaptive scheme, but if there are many cases if other self-adaptive schemes have same PDE's program, PDE program, then we will test and get a comparison.
Because in the abstract, it said it performs better comparable to self-adaptive pins.
Yes, there will be some other equations as below. The cell additive equation, the case in the cell additive pins.
I guess my point is that they should be compared for all these problems, right? I mean, not just selectively comparing.
Okay. This is a good suggestion. Okay.
But Michael, I think these errors 2 10 to the minus 5 is difficult to get with we use self-adaptive weights all the time and we don't get this error. So there's something clear, there's something here now. The question is what Nat asks, what contributes to that? I don't know if Shaoling can answer why we get, like, for this problem, why we get better results. Shaoling, can you say?
Oh, yeah, I can say.
The interpretability that Nat asked. Yeah.
Yeah, I think that's because he trained the weights for each training point. So the imbalance of the gradients among all the training points has been like balanced. That's why he can learn the solution for the inner interior better than these HPV pins.
Yeah, Zogren put on the chat something that we usually visualize the weights, self-adaptive weights. So if you guys can do the same thing here after you train, that would be useful.
I think Guangtao has plotted the distribution of the weights, but he may not have put that in this presentation slide. So.
Okay. All right. Yeah, the good results. It's not. We're just trying to understand, Shaoning, why do you get? You're not just lucky. You get good results. So must be a reason.
Oh, yeah. Okay.
Go on, Guangtao.
Okay. Thank you.
Thanks. Yeah.
Okay. Thanks. And we have more test results on Poisson equation, and here is the test case compared with revisiting pins. We test Poisson in 3-dimensional and even 10-dimensional, and compare the results with Dibley's method, and the results are shown here. Yes. All the results about Poisson equation. After Poisson equation, we test Helmholtz equation, which is very hard for pins to solve, and we use the sign function to construct the solution and external force QSY. And then we compare our results with pins, learning rate annually and learning rate annual MLP, and the error is 1/50 of the error of M4. Also note that DASA can adjust the weights itself, but M4 has to compute the weights manually. And here is the results. Yes. After we finishing testing Poisson and
Guangtao, go back. You are too fast for us. You have too many results in one slide, and not everybody. So go one by one.
Okay.
Like here on the column on the right, the first row is this uses the global weights of from Paris paper, right?
Yes.
So yes. On the table above, what is that called? M2. What is that?
M2 is the details I forget, but it's about the architecture of the neural network. Yes.
But pins M2 is which one? Which from the row below it is it?
You mean the pins? Pins is the first row, and the yes, in the paper, the pins is the first. The results are in the first row. Yes.
And then using learning annealing is which column is on the table?
Is the annealing is the pins M2. Yes, the M2. Yes, M2 model.
And then what's the last
with-
one? Yeah.
Yes, is with the M4 model. Yes, the difference of M2 and M4 is the wide they have different width and depth. Yes. And this may be a mistake. Okay.
George, I think the results of DASA-PINs are on the left. So
Yes.
yeah.
Yes.
Okay. Keep going.
Okay. After we finish testing the Poisson and Helmholtz, we move on to a classical problem, Lie-driven cavity. We solve two dimensional steady-state Navier-Stokes equation on the square domain. Only upper wall is moving from left to right, and the other three walls are stationary. There is a main vortex in the middle. If we increase Reynolds number, there will be a eddies near the bottom wall. We compare results from DASA with a list from pins and M4 pins. Also, we increase Reynolds number and compare results with the cell adaptive pins. The results are shown here.
So this is the self-adaptive pins that we're talking about, right? Before.
Yes, we test we test the result on cell adaptive pins by ourselves.
And do you have a plot of your weights versus their weights, the distribution that you can show?
Not yet. Yes, no, we haven't plotted ways of control. Yes, because it has the scale operation. So the weights the distribution of the weights may not as we want. Yes, but you can adaptively adjust during the training.
And what happened when you try to run? I suggest that you run Reynolds number 1000. What happened to that case? Your code didn't converge?
No, it cannot convert if we just use the DASA-PINs. Yes.
Okay.
We demonstrate the accuracy and efficiency of DASA for time-independent problems, and now we will show the performance of DASA on time-dependent problems. Yes. Alan Kahn is a challenge for pins to solve. It has shown nonlinear and is very stiff. Here we use diffusion coefficient 1.e-4, and DASA achieve 7.e-5 L2 error, which is the best amount of the versions of pins as far as we know. The results are shown here. Wave equation is another challenge for pins, especially for ones with multiple frequencies. We compare our results with the cell adaptive pins. Yes. The next equation is the diffusion reaction.
Can you go back?
equation.
Wait a second, Guangtao.
Okay.
Yeah.
Okay. Sorry.
You need to learn how to analyze your results better. Shouting, you need to do a better job on.
Okay.
How many times did you run your DASA to get the standard deviation?
We
It's pretty stable.
we train with about 100,000 iterations using Adam, and the time is about as the same as the best pins. Yes.
How many initializations? Because you get the I see standard deviation here on the error. So you tried 5 times. How many times did you run it?
5 times. Sorry.
Shouting, you have plus minus a standard deviation. How did you get that?
So Guangtao, he asks, how many times did you run your pins to get this standard deviation? 10 times?
10 times.
Oh.
standard deviation. You need to run the pin many times to obtain the standard deviation. How many times did you run?
他就是问你跑了多少次这个 pins 得到了这个标准误差，这个标准差。
就10000次，就10000次啊，就在这里。
No. Here is the number of iterations.
How many get the absolute error? How many points?
No, how many? Well, you how many
Well, yeah, I asked him to do this. I think he ran 10 or 20 times the same number as that in the self-adaptive pins. We will check that after the presentation, okay?
Yeah, Shaoning, basically the question is how stable is this?
Yeah.
It looks very stable if the standard deviation is so small. So you basically land on the same minimum every time. So it would be nice from one run to another to actually compare the distribution of weights. This will give us a feeling of what's going on. I think you get good results. You don't know why you get good results. So we have to go after the why.
Oh, yeah, we will check that. Okay.
Please continue.
Okay, thank you. And the next equation is the diffusion reaction equation. We use solution with 4 frequencies here. Then we compare the result with the G-pins. The error of DASA is 1/30 of the error of G-pins. Yes. And this is the case of adversarial diffusion equation. We also compare our result with HPV pins and achieve better performance. Next, we will have a look at the performance of DASA on complex domains and solutions with discontinuities. We test DASA on different geometries, triangles and circles and etc. Here we only show the result for L-shaped domain. Then we will give the result of DASA solving adversarial equation with discontinuous solutions. And here are the numerical results of DASA solving position on L-shaped domain. And it can be seen that DASA pins was better than HPV pins. HPV pins here relatively define the mesh near the corner. We also consider the adversarial equation with a discontinuous solution. It can be seen that DASA pins work well. And we also consider another adversarial equation with discontinuous solution. You can see that DASA pins work well, yeah, compared with the cell additive pins. We have shown that DASA works well on for 4 problems. Then how about inverse problems? What if we have unknown parameters in the equation? And can DASA infer the parameters accurately while solving latent variables? For Navier-Stokes equation, the ability to infer the unknown parameters better than original pins. And one-dimensional Allen-Kahn, we also compare our results with VC-pin method. VC-pin is a method similar to the causal pins. They use ways to scale loss at each time step. DASA can infer the parameters with both the clean data and the noise data. After we finish all the tests, we also look into the possible reasons why and how DASA can work so well. For leaf-driven cavity, we plot the gradients of the network of DASA and compare with the baseline pins. We found that DASA can adjust the imbalance of the gradients even more than pins. The yellow line is the gradients of the residual loss, and the blue line is the gradients of the boundary loss.
This is Kamal here. I have a small query. In the subnet, the output is added to the data loss or the pin loss in the inverse problem.
We plot the gradient finally, and you just use the pins loss. Yes.
So the inverse problem will have some data points also. So loss is, do we have the loss function?
The loss function is the simple loss function. We not the residual loss. Yes.
So Guangtao, and then come out ask your subnet for the weights. Are they just for the residue loss or for the data loss as well?
We just use to adjust the residual loss. Yes.
Just residual loss.
Yes, just residual loss.
So you treat every data, every observations equally without sub-adaptive weights, right?
Yes. Yes.
Okay. Yeah.
Thank you.
Thank you.
And we also plot the NDK eigenvalues. We solve the Allen-Kahn equation, and KUU is the kernel of the output of the network. KRR is the kernel of the governing equations. The NDK eigenvalues of DASA distribute more evenly than pins, and the dashed line are DASA, and the solid are the best pin, and the red line are KU, and the green line are KRR. And here is the summary of the relative L2 L of DASA, solving various PDEs compared with other pins, including HPV pins, G pins, cell additive pins, revisiting pins. Also, we compare the computational cost of DASA with baseline pins. It shows that DASA does not need extra time to train.
Can you explain what the numbers are? In 1D Helmut says 1.10. What does that mean?
Okay, is for example,
for the cost. Go to the cost. The right bottom.
Okay, the cost.
1D Helmut 1.10. What does that mean?
We train the DASA pin with the same iteration, and we train the pins with the same iteration, and then we divide them, and we have the relative computational cost, and the iterations, the number of iterations, almost all the case we use the same as the base pins need. Yes.
So 1.10 means you are 10% more expensive than pins.
Yes. 10. Yes, you are right.
So that's similar to self-adaptive weights. I think they.
Yes.
Right, Kamal, or some data, do you know how much the self-adaptive weights adds?
I got 5% actually.
How much?
5%.
5%, yeah.
Yeah, but your results are better actually, but that 5% is you can't compare because they have different accuracy.
So Michael P from Utah, in the lower bottom, he has the comparison that you asked with the self-adaptive weights. So
yeah.
So it is significant. And the cost is probably similar. So it clearly is a very good method. It would be interesting to know why and when and why it fails also in cases that the pins fail. And so go on, Guangtao, you're done?
Oh, okay. One more slide, and this is the conclusion. In this work, we develop a pointwise loss weighting strategy, and DASA-PINNs. We demonstrate the accuracy and efficiency of our scheme by solving various PDs. Both forward and inverse problems are consistent. In the future, we will apply DASA to problems in application fields. We will combine the DASA with neural operators to learn the operators. Here is the reference for our work, and that's all. Thanks for your attention. Thank you. Okay.
Good work, Guangtao. Fei Chen Hao.
Thank you, Professor George. Yes.
Do we have a question for our speaker?
Can I ask a question here? So you use a neural network to find out what are the weights, right? And you call this the subnet, the subnetwork.
Yes.
However, you apply it also to problems that have these weird domains, like the L-shaped domain. So how do you know that you can actually represent accurately the distribution of weights using a network if a network in general has trouble with this kind of geometries? You see,
Yes.
You see what I'm saying, that in the original self-adaptive weights, you just compute the weights on a certain grid, right, of points. Here you use a network to represent the weight. So I'm afraid that if you try it on irregular domains, you will end up getting into trouble.
Okay. This is a good question. Yes. I will test after the presentation. Yes.
Okay. Because these are very nice results, like everyone else said. So I'm just trying to understand why it works, 1 to 2 orders of magnitude better, and what are the limitations of using a neural network to represent this weight field, right? It's a whole field of weights now.
Hold the weights.
It's a continuous. You represent the weights as a function of space, right? So yes, so it's not just evaluating the weights on a grid, but you actually represent it as a function. So if you have an irregular domain, I expect that this function may be difficult to represent with a neural network. Obviously, it's not so far in the examples that you have tried. I'm just trying to understand.
Ulysses told me that they have an updated version of their, and they're using Gauss random fields. Gauss regression. Sorry, they're using Gauss regression so they can have a continuous field. Yeah.
Okay. And it works.
So it would be interesting actually to look at those two formulations, because
yes. Okay.
Lulu, what do you think? I mean, with GPIN, we try hard and RAR and so on. So these results look good. I mean, uniformly, they did a lot of cases. What do you think? Where's the magic?
So if we compare with the self-adaptive pins, so by using the network to represent the weights, could have some advantage. For example, because during the training, everything has randomness. If every single point of the weights is independent, probably have more fluctuation and somehow unstable. But if with a neural network, then definitely will make the training more stable and make the weights adapt more nicely.
Yeah, that's why I was interested to see the standard deviation there. Actually, that would be also a good study for all the cases to have standard deviation, how stable this is compared to self-adaptive weights, for example. Xiaoning, that would be something to consider.
Okay.
Any more comments? Everybody's using pins and self-adaptive weights and so on. Any more comments? Can you guys be better than Guangtao? So Guangtao is now has the world record.
Oh, but I have another small question. So for your network, do you limit the network, let's say, what's the maximum value, what's the minimum value, or they can increase? Because if we keep the training, right? Because green ascent, if we keep training, then probably the weights will become larger, larger, and larger. Do we have a threshold or something?
Okay, you mean about the influence of the body weights? Yes.
Yeah, the weight, yeah, the weight network. Or it's unbounded, it can go to infinity.
We also test the result with the body weights, similar to the cell-adaptive-pins, but it doesn't work so well. Yes, these are the numerical results. Yes.
Yeah, Guangdao, I have a follow-up question to
Okay.
Lulu. So I think did you do any normalization to the output of the your subnetwork? So, because if you times every weight, times the output of the new network, the subnetwork with some constant, then the loss will increase, but the optimization problem for the backbone network will be the same. So instead of the upper bound for the lambda, I think it should be some normalization for all lambda.
Oh, it's only if you look at the bottom, this normalization.
Yeah.
Yes.
Oh, I see. Yeah.
Yeah,
Then he doesn't need upper bound for lambda, right? This normalization.
No, right. That's the thing that we usually have to cap it, right?
Right.
We don't need to cap it because that's what, and that's tedious, and we have to add it. But yeah, that's interesting. Guangtao, is the code on the web? Is the code available or not yet?
Sorry.
The codes you use to generate results for this paper, are they already online?
Yes, I realize the code. Yes, you.
No. We mean the codes, the Python codes you use to generate results. Are they available to the public?
Haven't yet. We will open the code after the submission to the journal. Yes.
Okay.
Thank you.
So that
I have a question about updating. Is the
go ahead.
Is like the learnable, I mean, so the subnetwork that controls the weights has like a learning rate or ability to update the weights. Is that comparable to the rate of change of the self-adaptive weights? Like what is the, how are they comparable when you test this? Like how quickly the weights can change over so many iterations?
You mean the learning rate of the subnet?
Yeah, I mean the learning rate, of the subnet, is it analogous or comparable to the rate of change of the standard self-adaptive pins?
Okay, we use the learning rate annually here. Yes, we use the initial rate as 0.01, and then we use the learning rate schedule strategy to update the learning rate and without a specific design. Yes.
Yeah, I guess it's more to the point of George with plotting the two things, plotting them over iterations as well, like in an animation to see how quickly it changes. Maybe this one really quickly converges to the right weights, whereas self-adaptive pins might take longer. So I think that would be very insightful to see the mask of the weights for this and the other one as they train through the iterations.
Sorry, I can ask. Pardon.
So you have like a plot of the weights, right? over the domain.
Yes.
Yeah. So the plot of the weights for your method and the self-adaptive method, as they change through training. So you can see how quickly it converges to the right weights.
Okay.
If this method converges much quicker or something like that. I think that would
Mm,
help explain the difference.
the difference. I think this is a good question, but can we discuss more detail after the meeting? Okay.
Sure. Yeah.
Thank you. Okay.
Yeah, do we have any questions?
Guangtao and Shawnee, thank you very much. I know it's 2 a.m. in China, so thank you for staying up late. So this was very informative, and
Okay,
let us know when the code is available. Thank you very much.
Okay, thank you.
All right, let's move to our second talk. Our second talk is given by Adar Kahana, who is currently a postdoctorate research here at Brown University. Before joining Brown, Adar worked as a data scientist at Microsoft, and he obtained his PhD from Tel Aviv University in Israel. Without further ado, Adar, I don't have to say welcome. Yeah, you may want to start. Oh, can you share your screen or?
Not yet.
Oh, let me make it go.
Yeah.
Yeah, you can try it now.
Let's
Just
see.
cue the hook.
Oh, now it looks better. But let me know when you can see my screen.
Yeah, we can see the screen. Yeah.
Perfect. All right. So a little bit about what we're going to have today. I'm going to review a paper by this list of authors that's given in the first slide. I put a hat in the background. It's going to be the main result that we are going to talk about today. This is a very cool paper. I will say in advance that in this I'm going to kind of review 3 papers at once, not review all of them, but like the main paper, we're going to go through all of it, but we are going to have a hint about hints and another hint about the paper of spectral bias, the original paper of spectral bias by the group of Yoshua Bengio. So there is going to be quite a few theorems and lemmas and a bit of mathematics, and quite a bit. I'll try to do it in a very approachable way, though I have to say that both big papers, the original spectral bias paper and the current paper we are going to talk about, have tons of proofs. So I'm not going to go into them. I'll give some intuition, but for anyone who actually wants to go deep into the math, you're more than welcome. I certainly did. It's pretty interesting, everything that's going on there. And I'm sure everybody will find it very interesting as well. Right, so I'll start with a bit of motivation. It will be very brief, very short, just to be a bit sarcastic about this, what we're trying to do here. Then I'll show what is spectral bias. First paper of spectral bias. How did they define it mathematically, and like not just the notion of spectral bias, more of like what it is. How can we show that actually? Then we'll do the same, but in a different kind of formulation that has been used by the new paper. And then we'll jump for some analysis of for shallow networks, which is they chose that in order to more easily show and prove how they can remove spectral bias, which is basically what they tried to do, and then show some experience and connect it to hints. So, right, the motivation. Basically, that's it. Spectral bias says that low frequencies are learned faster via training by stochastic gradients. I'm sure lots of you already know that, like in the plain definition, or this, let's say, this populistic kind of way to define spectral bias. And now the important things that the important result of the new paper that I'm going to review today is that based upon this theory, we predict that a simple modification of the ReLU activation function called the hat activation function will remove, and I want to emphasize it again, will remove the spectral bias of neural networks, which is a big, big claim. Right. And basically, I'm going to like try to lead you into the understanding how it actually removes it, like roughly removes, like not 100% removal, but there is some sort of removal of the spectral bias. But we need to approach it through the mathematics that goes behind it, and this is what motivates us. This is exactly why I'm presenting this paper today. Like, if this actually removes that and everybody starts using this hat activation function and gets way better training in all of the networks, then amazing, right? We are all very happy about something like that. So just to motivate you specifically for this presentation, we are going to revisit the definition of the spectral bias, cover the theoretical, the foundations that we need to understand how to remove it, and then introduce the hat function and how it actually removes it. And obviously we have to finalize with some pretty pictures of graphs showing that the spectral bias was actually removed. So what is spectral bias? The first paper of spectral bias by this group published in PMLR after I saw that they were rejected from ICLR, sorry, and then which completely surprised me, because this is a significant paper and it was written very well, and like, I don't know, I was very surprised. So it was after quite a while published in PMLR, only like here to 2019 was the time that I actually got it published. And again, I wanted the biggest claim of this paper is that the spectral bias is a tendency of neural networks to fit low frequencies faster. That's what they are saying, like explicitly. And then they are trying to, in this paper, make observations and analyze this phenomenon and show mathematically why it happens. So they didn't suggest any solutions. They just suggested the formulation, which is super, super, super important. Now, I kind of mentioned that this as an excuse for showing you this paper, as well as the paper I was supposed to review, because this is the foundation. The second paper actually is built on top of this one. They are referencing this paper so many times. They are, although they have a different like formulation for the same problem, they are actually making the same claim, but like in a different disguise. That's basically what they did in order to build all the mathematics, and then show that the hat function actually solved that is based on exactly what we see in this paper. So I decided to take a couple of slides and actually show what is spectral bias from the original perspective, or original point of view of this group who published the first paper on that. So where do we start? We start with formulating a neural network as a composition of layers. We can see each layer T is a hidden layer that takes from one multi-dimension to another multi-dimension. And between them, we have basically it's a big composition of functions. And between those layers, we have an activation function that is denoted by sigma in this formulation. And we can we will talk about different sigmas, but for now, and it will take like 20 slides until I get to the actual hot function, I think. So for now, for a long time, we'll deal only with the ReLU activation function, which basically takes the maximum values between 0 and the other components of the input. For fully connected neural networks, we have something that looks like this. We multiply the input by a set of weights and add biases. Right. Another thing I want to mention, this is the last, the last bullet here. In both papers, the big, most of the analysis is done for function regression, meaning that the input will be a scalar, and the output is usually a scalar as well. In this case, the general formulation is where the input is a multidimensional function. Like they are also showing some examples from MNIST, and MNIST obviously is in higher dimension than the scale, but the output can be looked at as scalar. They have a way to define this as a scalar instead of one hot vector of size 10, for example. So in most of the analysis, we'll have an input scalar and output scalar, and in most of the experiments as well. All right. Now we can start by looking at ReLU functions as continuous piecewise linear functions. If you composite a lot of ReLUs, basically what you are creating is a high dimensional continuous piecewise linear functions. This has been proven in Aurora, and they are showing that they show mathematically how this can be formed. Like each ReLU network can be formulated as a continuous piecewise linear function, and vice versa. Actually, each CPWL can be formulated as a ReLU network. Just a bit like if I took a deep dive into the mathematics behind it. How they actually do that is like if you imagine a ReLU network or a high dimensional continuous piecewise linear function, you can think of a polytope in space, like a high dimensional space. So it's kind of like an extension of a staircase function into a higher dimensional. So in 3 dimensions, we can already imagine some sort of I don't know, some sort of a structure that has like flat edges connected. So in higher dimension, obviously it's hard to imagine, but this is something like that. And their analysis is based on like properties of the edges themselves. Like you can the normals from the edges, things like that. You can define that, and then it's easier to make mathematical assumptions and lemmas and prove things based on the edges and their structure. And also things like we can take a ball and put it inside that polytope, and the largest ball will have a lot of good properties because all of the points that are connected and they're within the region. So this is the basis for all the mathematics that they did there. And another thing I want to mention, if we're already looking at this expression f of x equals the sum of like so this one here is the indicator function. It's each p epsilon is a small support of the output of the linear layer in this case, and we can look at it as like very a piecewise linear layers. And if we look exactly at this formulation, and I'm spoiling the rest of the presentation here. If we look exactly at this formulation, something should ring a bell. This looks like finite elements, right? Because we have compactly supported shape functions that are, in this case, linear functions. Yeah, and that's a very important observation we are going to revisit, that piecewise linear functions are composed of multi-dimensional linear functions and essentially connected to finite elements. So just to review what's going on here, indicator I already said, W epsilon is kind of like using the ReLU on, but when we think about the ReLU, we take the output and just put it into a max function, right? But we can also do just take the weights related to the outputs that are 0 and just take all of the weights in that column, for example, and make them 0, right? So if we do that, when we multiply it by the input, we get exactly the same output. So this is how they define W epsilon. It's basically taking the zeros on the columns that are inactive. Let's call it that. Now, getting more interesting, we need to talk about the Fourier spectrum. Why? Basically, the spectral bias is tightly connected with frequencies, and the proper way to define the frequencies in high dimension, or at least the way that they chose in the paper, is the Fourier spectrum of the Fourier frequencies. In these definitions, I'm sure all of you are familiar with. It's like 101 for Fourier analysis or harmonic analysis. And this, I really like this notation and this way to define frequencies. It's very old school. In the next paper, we will see something that looks a bit different, but essentially they are the same. And also this gives intuition of what the Fourier spectrum is in high dimensions. In this case, K, or in this case, bold K is the frequency, bold X is the input in the spatial domain. We can compute the Fourier coefficients F tilde, and we can compute the Fourier decomposition of every signal in high dimensions. Now, an important observation is what happens if we take the Fourier decomposition of Fourier transform of piecewise linear function or continuous, the CPWL, what we talked about in the last slide. We get an expression that looks like this: I times the sum of W epsilon K over the magnitude of K squared and multiplied by the indicator functions. But notice the tilde there. It's the Fourier coefficient of the indicator function for that specific frequency, right? It's given in the like here I put exactly what is this Fourier coefficient of that. So did I want to say right? This basically makes things easier to analyze, because we have a formulation of the Fourier spectrum of the function, and we know how to compute it, and we know how to plug it, and we can create a lot of expressions from that. Okay. Right, so now it becomes more interesting. We have this first lemma where P is a polytope in hyperspace, and we can think about it as a compact space holding all of our observations, let's say. And then we can have a Fourier composition for this specific polytope. Right, it's more complicated than looking at just an indicator, like as just a support, because now we are sort of cascading lots of supports into one big polytope that is a structure in high dimension that is, yeah, it has flat edges, but we need to take care of all of them all together, and we want to know what is its Fourier decomposition. So basically, this lemma helps us do that. And we can see the important thing is that we have, or two important things. We have Dn, which is just a set of functions, and then we have n codimensional faces that are synergetically working in order to give us this definition. And I'm showing this lemma basically as a support for the next theorem, which is the main result of the first spectral bias paper. This is the main result that everything relies on, basically. So let's go over it. The Fourier components of the ReLU network, F theta is basically our network, and theta are the parameters. So the Fourier components of it look like this. We have Cn, which is a function of the parameters, and is multiplied by the indicator function of some Hn, which is a union of all the subspaces orthogonal to the n codimensional points from the lemma. Now, why is it so important? First of all, okay, I'll just move to the next slide because it has all the observations, and I also copied the result here. The first observation says that the decay of the ReLU networks is highly anisotropic, meaning that we have, for several frequencies, we have a decay that is minus d minus 1, and for other frequencies we can even have k to the minus 2, which is completely different and creates different decay of the coefficients depending on the frequency, which already gives us some intuition, right? These single observations, some may say it gives everything already, but it gives us a lot of intuition, at least for me, about this spectral bias phenomenon. Like if we have different decay of the Fourier coefficients for different frequencies, it already kind of seals the deal. It already kind of tells us what's happening here mathematically. And yeah, the second observation is super important as well, because the denominator is not enough. We cannot only count on the denominator just giving us different decay for different frequencies. We also need to take a look at the numerator. And there's another lemma, which I decided not to go into here, just put it as an observation. The numerator is actually bounded by NF times LF. NF is the number of linear regions of the big polytope that we are approximating. And LF is a Lipschitz constant that describes the network. So, and the important word here is bounded. Since we can bound the numerator, then we're basically only dependent on the denominator to dictate the decay. Now, from this, like literally a paragraph after showing this, there's the theorem, then the observation, and then a paragraph later, the authors claim, now based on that, we are going to show that lower frequencies are learned first. So yes, this basically gives us the mathematical foundation of why this phenomenon happens. Again, if anyone actually wants to go and see the proofs and see how it actually operates, there are tons of them, and it's like a maze of understanding all the proofs and lemmas that lead to this one. But yeah, but they are very interesting, and you can have a lot of insights throughout understanding the proof of this about both spectral bias and trying to understand polytopes in hyperspace. And here I'm giving just the bottom line. So yeah. Now that we understand that, and we kind of have an understanding of mathematically what is spectral bias, let's see it empirically. This is from the okay. This is the first experiment from the old paper of spectral bias. Some of you probably saw these images quite a few times. So the experiment is pretty straightforward. We have a set of frequencies taken to be k equal kappa from 5 to 50 every 5. So we have essentially 10 frequencies. The amplitudes are for now taking as 1. Like in the second experiment, they are actually varying the amplitudes, get the same results. So I decided to skip that here. Then we have some phases added. And as I said earlier, most of the analysis is done for function regression. In this case, our function is just a compilation or a sum of sine functions. Lots of frequencies happening there, like 10 frequencies actually. And we are trying to approximate lambda. So the input is one-dimensional number z between 0 and 1, 200 points. The output is lambda of z. And we have 6 hidden layers of size 256. One last thing, the phases are randomly distributed between 0 and 2 pi. And the first thing to see here is that if we look at the Fourier frequencies given by this, like we have a function that is basically a signal. We can easily compute the Fourier, the composition of that using FFT or something like that, whatever we want to use. It's very simple. And we can normalize it by the amplitude. In this case, it's 1, so it's meaningless. But if we have a different experiment, we should actually take that in account. The important thing here is the vertical axis, which is the training iteration. Training iteration starts, it means that we in every epoch, we're trying to figure out the error in the frequency domain. We're computing the signal that the network outputs and compare it to the actual signal that we can compute. And the colors here are exactly the errors in the different frequencies. So we have 5, 10 until 50. Each frequency has the error over time, and we can see that the error, the ratio is very close to 1, meaning that they have. Oh, sorry, I didn't. I forgot to mention. We are taking the coefficient here. So for a coefficient, when we take the abs, we get the amplitude in that frequency, and then we take the ratio between the predicted amplitude and the correct amplitude, which is 1. So we want this ratio to actually be 1. Okay, and you can see here for the low frequency of 5, we have from the beginning a ratio that is very, very close to 1. However, for the higher frequencies, we have a big error here, meaning that essentially, again, lower frequencies are learned faster than higher frequencies. This one actually shows this, shows it over time by the entire signal. Like this is the signal that they were using. So at the beginning, we have something that learns the very, very low frequency here. Then we have like a bit higher frequencies after 1,000 iterations. Then after 10,000 iterations, it looked like this. Some of it, this is a very interesting phenomenon that I found. Like some of the high frequencies were already learned, some of them were not. And since this is a periodic function, I would expect having not so good results. But this interesting thing in the middle kind of was perplexing for me. I didn't really understand why that happened, but we can attribute it to the optimizer, and there are a lot of things that can actually happen to make that blip in the middle. But what I thought about doing, instead of like guessing what's going on here, just reproduce their experiment. Like they are a scientific paper, they've made everything available, so I can reproduce even the code. I just went over their code, and they implemented in PyTorch, so I decided even to take it to TensorFlow to have a bit of more difference in terms of the environment, but still the exact same parameters, and I got much different result than them, to be honest. After 1,000 epochs, I get something that looks like this, which is kind of half-half. I don't know how to interpret that. And then like I did get something that looks like it's learning first the low frequencies, then high frequencies, just not exactly like what they achieved. I still need to take a look why it happens, but yeah, I get the same interesting things that I was, or let's say otherwise, it didn't give me any explanations. I just yeah, get the same things here. Yeah, I may investigate it a little more to see what's going on there. Okay, now, first of all, maybe I'll stop for questions if there are any questions so far. All right, cool. Either everything is super clear or nobody understood anything and they're scared to ask. So I hope the first one. Right. Okay. So back to the paper that I was supposed to review. So I will start by explaining how they approach spectral bias, because it's a bit different. They have the notion of frequency taken a bit differently than the other one. First of all, they wanted to kind of extend the formulation. I showed you the Fourier formulation, which was again old school and nice, and everybody knows that, and it's easy and approachable. And they wanted to kind of extend it to support different kind of decompositions or different kind of projections. So they define it with some kernel. Usually, in most cases, they claim that in most cases the Gaussian radial basis function kernel will be the ones to use because of its resemblance to sinusoids, and it can be a good proxy for like representing the sparse data in high dimensions. So it's been used in many of the experiments and many other papers. So they claim that this can be used, but they also claim that you can use a lot of other bases in or kernels, sorry, or the kernels. And as you can see here, the kernel is taking from the data points to the data point. So X is basically the space of all the functions defined on the data. We can define any kernel that will satisfy a function between data points to data points. Okay, next. So in this case, they define the composition in a different way in terms more of the error. Okay, so let's assume there exists some basis of eigenfunctions, phi 1, 2, as many as you need, with corresponding eigenvalues, and they are all suitable for some operator which is somewhat related to the neural network itself, which the neural network is denoted by f theta of L. L will be the iteration later, and f theta star we denote as the empirical minimizer, meaning that like after the network has trained and we decided that it's trained sufficiently well, and this is our minimizer, so this we will call f theta star. And as you can see, where the important element that we're seeking is the difference between the per iteration operator, which is the network, or yeah, the function, which is the network, and it's how it's different from the let's say the empirical minimizer, the final network that we want. And since both of them can be projected onto that space, space that has been spanned by the basis of eigenfunctions, we can look at this subtraction as a summation of some coefficients times these eigenvectors, eigenfunctions. Yeah, and basically in their notation, spectral bias means that the coefficients of these alpha IL decay more rapidly for small frequencies, and you can easily observe that from here we are seeking the error between the network at some stage of the training and at the end of training. And if we know that it has some coefficients in some space, those coefficients of the lower frequencies denoted by I are decaying faster. Low frequencies will have smaller errors faster. Right. So given this notation, we can make a lot of mathematical like procedures in order to actually show that this happens. So we start by setting up a very simple experiment. If you notice, this is a very shallow ReLU network. This has only one layer. Also, if you notice, the weights multiplying the x here are taken as 1. And the bias terms are I over n. N is the size of the, sorry, n is the width of the network. So, and the trainable parameters here are AI. AI here is kind of a parameter that we put after applying the activation function, and sigma here will be just ReLU for now, right? So I do have to say one thing. Throughout the paper, all the results, and when I say results, I mean the theorems and the lemmas they proved are for this. They were a bit like other proofs that extended, but the main result is based on this simple case for shallow ReLU networks. So everything that they also showed empirical results for deep networks, but I think that for a general case there needs to be more math. I haven't seen. Maybe I think that some extensions need to be done in order to support mathematically other things. But the more important thing is that the interesting theorems are, this is sufficient to prove them. So they did that, and you'll see how interesting is that. Is it going? So for this neural network, we are also taking the mean square error loss, which is given here as a continuous function, and there's a reason for that. The reason will come in the next slide. So yeah, we just take the standard mean square error loss over the so u, the function u that we're taking, you'll see it's following the first paper, so it will mostly be like compilation of sine functions in a lot of frequencies. So we can take it as a one-dimensional function that receives inputs between 0 and 1, and outputs. The network will output the regression value. Right. So taking the mean square loss is very natural in this case. Now, the first thing we want to show is how it's connected to finite elements. So there's a lemma showing that the mean square error loss that I showed in the previous slide, and I insisted on taking it as a continuous one, because in finite elements we have the lemma that we can show. We can basically represent the loss by multiplication of the inputs by a mass function and the bias term that is given here. While the and these, I'm sure everybody on call that ever interacted with finite elements somehow have seen these. Yeah, like assuming that these are the shape functions based. This is basic finite elements. And I want to state something here. Matrix M is positive definite just by just getting it from the finite elements formulation. And this will, at the end, when we talk about hints and things like that, this will be an interesting point to talk about, like an interesting thought, because yeah, this kind of it's something to keep in mind. All of the analysis was done for M sigma that is positive definite, and then if we have a matrix that is not, then maybe we should create
it's
different.
well known, stiffness matrix and mass matrix. That's what you have. It's a stiffness matrix. M is the stiffness matrix. Yeah, okay. And B is the mass matrix.
Yeah, I've just later we'll talk about stiffness and matrix and mass matrices that are not necessarily positive definite. I'll talk a bit about it. So just wanted to plant the seed and
keep going faster.
Yeah, sure. Okay, let's go fast. Right. So how does this connect to spectral bias? We have this theorem, which will follow us a lot in this talk. Basically, if we consider the network that we defined, the very simple shallow network that we defined earlier, and we use a gradient descent to minimize the loss and learn the function f and n. We have all the setup. Yeah, I'll just not. You guys can see it from here. Then we have some basis function phi j that looks like this. This is the exactly the part of the network that we defined earlier. Now the theorem says that we can, if we consider this expansion that we are interested in, and I showed it earlier, then the coefficients satisfy this term. It means that these are the coefficients I talked about earlier. I is the frequency, L is the iteration that we are at right now. So this is exactly how it's written in the paper. I am not sure if that's completely correct. I copy pasted it exactly and checked this like 100 times. There may be 0 here. I'm not exactly sure, but then what we want to focus on is this term here. The difference in the eigenvalues of the expansion, okay, the lambda 1 are the eigenvalues of the mass matrix. This element will be tightly connected to spectral bias because this element actually dictates the decay of the errors in each frequency, right? So basically, we just need to show that this element, lambda I over lambda n, is how it decays for each I, or how is the decay dependent on the frequency. Okay, one theorem was produced for Relu, and you can see here the lambda, the ratio between lambda n and lambda j is n to the power 4 over j to the power 4, which means that for very low frequencies j, we get let's say very slow or very big ratio, right? This we can prove it using this theorem. Also, like the couple of you can see everything here kind of relates to finite elements. So we have this differences matrix here. If we take the composition of a squared plus b, we get something that can bound all of the coefficients of the eigenvalues of this matrix, and these are applied. These are connected to the eigenvalues of m sigma, and this is how we actually can prove this. We just take lambda k and lambda n, and everything just is straightforward from there. But proving this theorem is super difficult and it requires like 7 lemmas. Right, so I'm just going to go ahead and continue, assuming that we're okay with that. This I found very interesting, so I wanted to show you that. Another thing that we can get from finite elements is like the perspective of smoothness. We can use this theorem that is coming also from like basic things in finite elements. If we take the derivative of the eigenfunction squared over the eigenfunction squared, it goes as n to the power 4 over j to the power 4, which basically means that higher frequencies are less smooth, or yeah, lower frequencies are very smooth, higher frequencies are very the opposite of smooth. And okay, I think this is all I needed in terms of introduction to the paper, to how they define.
Adar, sorry, I have a question.
Yeah. Yeah.
So I see here that there is this very specific form of the bias, which is I over n, right? Minus I over n.
Yes.
And it means that as you go to higher frequencies, you get a larger bias.
Right.
So what they actually prove is that there is a spectral bias for this very specific type of neural network, but we have no guarantee that the bias in real networks will follow this very structured form of I over n.
Right. Okay. That's excellent. I have 2 things to say about that.
Okay.
First, n is the width. So they kind of in the paper they mentioned how this term is actually taking into account, like you can wider the network in order to make it more appropriate and get the same decomposition. However, the second thing I wanted to say is that yes, I think or I feel that this is very, very, very handpicked, and there are a few. When I was reading this paper, I had a lot of things like exactly what you said right now. Like I'm thinking to myself, yeah, this will work only for this specific case. What happens if we change that? Yeah, there are things like that which I don't really have a good answer to. I do think that if we want the most general case, the more math should be involved.
Right. The question is whether you can, for more general cases, whether you can guarantee the positive definiteness of the matrix M.
True.
So that then you can get the eigenvalues and the eigenvectors, etc.
Yeah. I agree. I completely agree.
Okay.
Yeah.
All right. Thank you.
Yeah. Okay. So after reviewing the math for this shallow ReLU networks, let's introduce the man of the hour, the hat function. So basically, if I oversimplify this paper, and we can ignore the math, we can ignore all the conjectures, all the lemmas and theorems and everything. If I'm oversimplifying, they are just saying the hat function is better than ReLU. If you use hat instead of ReLU, you will get no spectral bias. All the frequencies will decay at the same time. You will get faster convergence, and you will get not necessarily better convergence, like you not go into lower loss values, but you will get faster convergence, basically. That's the claim. One thing they did mention is that we have to use a scaled hat function in order, like, because the data can be in different scales, and when you push it into a ReLU network, especially a deep ReLU network, you may get different polytopes in space that you actually want to accommodate all of them and not have, like, because in ReLU you have the left part is 0, so you don't care, but then you have a linear that goes to infinity. Here you have a triangle, and this triangle is also chopped, so you have to somehow accommodate for all the values that you're going to receive. So for that, you have to add this term here, some scaling factor, yeah, and this basically gives you the formal definition of the hat function they used in the paper. Now I copy pasted this theorem again, so you don't have to reread it. Just take a look at this guy, the n to the power 4 over the j to the power 4, and now same theorem, but when I change the ReLU into the hat function, what they proved is that lambda n over lambda j is actually of order 1. And yeah, this is the massive, or the biggest, the big result of the paper. This means that the eigencomponents of the error decay are decaying at roughly the same rate, and this is the claim for removing spectral bias. One important thing to mention is that it's O of 1, it's not exactly 1, so there are still inconsistencies, and there are some frequencies that are learned faster than the others, but very marginally faster, not like with the ReLU, where it's completely different. Okay, so I just wanted to copy paste again this theorem, which was the main theorem here, and I just wanted to like summarize what's happening here. If we look again at this term that I said that is like, I think it's the most important one that dictates the decay. So if we go back to the ReLU, this will be equivalent to n, like j to the power 4 over n to the power 4, creating a very anisotropic decay. But if this is O of 1, this is O of 1, for every I, we will get basically the same decay. And this is a summary of everything I wanted to show you from this paper, basically. So from now, we're just going to see some cool results and some empirical experiments that show that. So before I do that, any questions? Cool. Okay. So first experiment following the other paper, very simple, just a compilation of sine functions, mean squared error loss, and we are okay. One thing important to mention here is that the error evaluation metric we're using is the difference in Fourier frequencies, basically. Yeah, the difference in the Fourier domain, right? So if we take the sine functions, the compilation of sines that we're using here, we can just FFT it. If we take the network, we can also just take the FFT. This is our measure of success, basically. I'm emphasizing it because later we'll have something different. So, and here you can see the green, orange, and blue are the errors in each Fourier frequency. So we have the first, third, and fifth Fourier frequencies. And here we have a tan H activation, here we have a ReLU activation, and here we have a hat activation. So if we look at it, I want to show it like this. This is what we kind of mean by uniform convergence of all the frequencies together. Like we can see that all of the frequencies here kind of converge at the same rate, roughly, for the hat function, obviously. For the ReLU, we can see immediately that are completely different. This is a completely different convergence. Another example.
Can I ask a question?
Sure. Yeah.
About the previous slide.
Yes.
This is super interesting and really exciting. I'm curious though that you still see a plateau in the middle plot for the blue line for the low frequency. So do you have a sense of all of this is still going to stagnate? Like eventually you're still going to get an order 1 errors that the anticipated, it's just that they'll all of the frequency will arrive at that stagnation at the same rate. Is that the right interpretation?
Right, and you're exactly on point. Like I was planning on talking about it in one of the last slides, because in hints we saw exactly that. But yeah, eventually we expect all of them to get to the same area, like the same area. Like if you train it for long enough, This is only 3,000. They cherry-picked these images. In the actual experiments in their code, they did 60,000. And obviously at the 60,000 mark, all of them coincide to the same place, and then you don't have any, you can see that all of, like, there's no spectral bias at 60,000 epochs. In the middle, like 1,500 epochs, you do have those stagnations and things like that, and the network is struggling with the higher frequencies.
It may have to do also with the shallow network. You try to approximate. I remember when Kahana was trying to approximate sine with a shallow network. You need so many neurons.
Mm-hmm.
So it depends what n is also for this.
Oh yeah.
For these experiments, yeah, for the absolute error that Nat is talking about.
I'm pretty sure it was 256, but I'm not. I need to check that. Yeah.
That if it's 256, that would be enough. Like if you compare it to like a nodal P1 finite element, right? That would be machine precision.
Mm-hmm.
Right?
Yeah.
So it should have the capacity to get it.
Yeah, because you can expand it to enough. Yeah.
You'll be surprised. You'll be surprised how bad it is actually. the single neural network. I don't know if Kahana is listening, but he did that and couldn't get a good result. But anyway, that's it is. I think it relates to the number of neurons.
Yeah, I'm checking it right now. I'm not sure they did not mention that in the paper. Okay, I'll check it out later. I don't see it in the paper. Maybe they put in supplementary. All right. So next experiment is 2D function, x1 and x2, getting basically the same results. So I'm just gonna skip that for now. In like still 1D, but with more frequencies, this is like exactly what they oh, sorry. Actually, this one is for a deep network, right? We have 6 layers. Each one is 256. And we are comparing, we are still regressing this kind of function with 10 frequencies and phases that are taken from different distribute, like the same distribution.
And
like
you can see the saturation
phases.
here. The saturation is much lower, right? So
yeah.
That was the issue.
No, but this is on machine precision. They the error in the frequencies they which heal machine precision. The main claim here was that, like, look at this. This looks horrible in terms of like frequency, how the frequencies actually converge, and then when applying the HUT function, this looks much more uniform, or the band of error frequencies is much more narrow. And they also tried less neurons. Instead of 256 per layer, they tried 128 per layer for the same setup, 6 layers, and they get a bit less, like less performance, worse performance, but still very uniform, very nice. One thing I wanted to mention is that they changed a lot between the experiments. So, for example, here they changed the number of the width of the layers, but they also changed the initializations, the learning rate, starting point, how much it goes down, and the number of epochs. Like, there were a lot of changes involved. And maybe another thing to consider for Nat's question is that, yeah, when you change so much, there may be differences. It's hard to keep track with like Professor, also you said about changing the number of neurons. Here they did, right? But they changed so many other things that I cannot tell you exactly, like, yeah, they changed the neurons and it's different. So lots of other things to attribute the changes to. This I don't want to focus on too much, but they just try this on MNIST. They used a Gaussian random radial basis function kernel, and they formulated as u of x is if a digit is right or a digit is wrong, and then over iterations they see that they get some sort of the same behavior also for MNIST. Yeah, and they used least squares for MNIST, so obviously the results, like in sheer accuracy shouldn't be the same, but like the convergence should be showing exactly how they deal with spectral bias. Okay, last part of the talk, I'll go very fast on that. Uniform convergence of modes. I'm sure some of you already know about what we did lately with hints. Hints also claims to do that, and but hints approaches it from a different angle. We said that we're going to exploit spectral bias rather than solve it or remove it. Hints takes a standard solver, formulates the linear system, and just goes iteratively, and sometimes it uses the standard solver and sometimes it uses DASA-PIN. Why? Because standard solvers are good with high frequency modes. DASA-PIN has spectral bias, therefore its tendency to work well on low frequency modes, and then we combine the two together in order to get something that's hybrid that will do uniform convergence of all the modes altogether. Yeah, basically what I said, DASA-PIN taking care of low modes and the standard solver taking care of high modes, we get something very similar to what they proposed in the graphs that looks very similar to what they showed in the other paper. And here is an exact replica of what I showed earlier with the, like here we have the very large difference between the modes, and with using hints we have very small and narrow, and all of them are kind of converged together. So this is from the hints paper. Exactly what there's you can observe with your immediately that there's a similarity. However, hints is trying to have the uniform convergence of what eigenmodes, because in the Fourier domain, they did something like this. We actually wanted to have the modes of the residual error converge to machine precision as far as possible. So there's a big difference between the two, and actually I should take it back. I don't know if there is a big difference. I'm not sure even if there is a difference, but we are currently not sure about the connection between those eigenmodes, and in order to do a complete Fourier analysis of the connection between the eigenmodes of the residual error and the Fourier basis that was used in that paper, we need to further investigate how are they. I assume there's some projection or a way to define the eigenmodes in terms of the Fourier basis, and then we can use all the theory from the spectral bias paper in hints. But for now, we have not discovered that yet. It's pretty interesting, to be honest. But I will show you how we did the eigenmode analysis for hints. Basically, we take let's say we have the linear system A, and we have its we can just compute its eigenmodes. Then we can set Fi to be the error in the ith mode by just this expression. Now, and then we can compute for each mode the error of that mode with respect to all of the other modes, right? Ideally, we would want to have an identity matrix, but actually we have something that is close to the identity matrix, and therefore we have some error. So this error is exactly what we decided to take a look at, what the DASA-PIN can handle and what is the tendency of frequency that the DASA-PIN has. And thanks to Enrui, we had this experiment of comparing what the DASA-PIN does once with a ReLU activation function, once with a hat activation function. And this is at the end of training. So the keen observers would see that there's not much of a difference here between the we're at the same number of eigenmodes that we're able to handle, and yeah, there's not much, not a significant difference between them, because in the eigenmodes spectrum of the linear system A, we do not expect the hat to perform well especially after training. Exactly as Nat said, if we look at it at the end, all of the modes have already mode errors have already reached saturation at the end of training, and we're at the empirical minimizer, so we essentially didn't get that much of a difference. But if we actually look at the if we actually look at epoch number 2000, which is much before the convergence, we can see like roughly here the wait, maybe I think I may have switched the slides. Yeah, here. Okay, I switched the slide. I'm sorry. This is the first slide. You can see like there's literally almost no difference at all. But on the 2000 epoch, we definitely see the hat function giving us better performance than the ReLU. We still need to investigate that because we had some things with the ReLU to take care of, but we do see that changing to hat already gives us some something different, and even if we don't have the math yet, something here happens. So we will further investigate that and see how it worked.
So I have one question here. So your
Yes.
this picture here, yes, this picture. So is this ReLU better or hat better? If I
Right,
see the diagonal, the diagonal seems to me ReLU is better, right?
So basically, we concluded as like what eigenmodes can the DPONet handle, right? And since wait. Oh,
Because red means it cannot handle, right? Blue means it can handle.
no, you're correct. I probably got nervous, and yes, the thing is, okay, I was right. This was the actual one after 2000 epochs, and yeah, you can see here. We can see that ReLU is struggling with the 6th mode, and hat takes care of it better, right? In here as well, like you can see that the errors here are lower, and then the hat. Okay, I hope does this one make more sense in terms of, yeah, it should.
Yeah, this one, but how about next one?
So the next one actually shows that they are practically similar. Even the hat is a bit worse, but this is at the end of training, so we do not expect the hat to be better. Oh, and actually in this one we had the loss actually jumped at the last epoch where we actually produced this graph. But essentially, if you look at it, like the modes that the network cannot handle are starting on the 8th mode in both of them. So we can basically conclude that the hat converged to the first 7 modes are okay, exactly like the ReLU, and at the end they are practically similar. That's the thing we can see from here. Yeah, hat, I agree with you. It works less well, like it's worse, but we did not expect that at the end to be better, so it's fine.
Okay.
Yeah. Okay, so it's a bit of over time. Sorry about that. If there are any questions, just go ahead, and thank you for listening.
Hi, Adar, this is Kamal from Brown. I put a paper in the chat. They have proposed 2 modification of ReLU. Any comment on those 2?
I should take a look at the paper. Give me a second.
Yeah.
How do I open? Okay, maybe I'll stop sharing then.
I think equation 3.3.
Okay, I'll share again. I'll open the paper and share my screen. Let me know that you can see it again.
Yeah.
Yeah, we can see it.
Cool. 3.3.
Yeah, 3.1 to 3.3 is modified ReLU they have defined.
Right. So it's funny, we just talked about like a composition of ReLUs earlier.
Yeah.
So essentially you can define the hat function as a composition of a couple of ReLUs, but I see here that you have the squared. So okay, so we had a discussion about what happens when you smooth a ReLU, right? We haven't tested that. But this is something that you might want to consider while you are doing like things related to PDEs. It would be very interesting because you so I haven't seen this paper, by the way. I'm currently like trying to figure out and connect some dots from things that we discussed in the past couple of weeks. So this ReLU is one thing, but we have this breakpoint here, and then you want to smooth it in order to support some more to fit data that it is more like pins and deponents. This will be very helpful. However, you're losing some of the nonlinearity. So we actually discussed trying something like this, like squaring only a part of the ReLU. This was actually something that we wanted to try because it makes a lot of sense. And yeah, I'll take a look at this paper and see what is their take on that. Just to summarize what I said, the hat function is basically a combination of ReLUs exactly like 3.3. And then if you take the square function, you can fit some specific data that will be more appropriate to fit like that.
Yeah, thank you.
So Adar,
Mm-hmm.
Since you asked the question, what is the difference between the way that they define convergence and how you define convergence because you use the residuals? I think there is an important difference there because if you take the residual and make it, very, very small, it does not necessarily guarantee that the solution that you get converges to the true solution, right? So if you go back to the PIN paper, where it was proved that it converges for solutions of certain PDEs, there was a final step, right? That after the residual has converged, then you have to show that what the output of the neural network converges to is the actual solution of the PDE. So it's like having a numerical scheme that knowing that it is consistent is not enough to prove that it is convergent, right?
Yes,
you also need extra stability there. So consistency plus stability will give you convergence. So there is a difference between these two definitions.
In convergence, yes, I 100% agree.
Yeah.
The main claim for them is that before convergence is what you are seeking. Like you are seeking like this L here. Oh, oops. This L here is like, let's focus on the first iterations of the solver, right? So, and what we were trying to figure out is like, okay, this L I can understand easily with the stochastic gradient descent, right?
Right.
But for a machine learning based linear system solver, that would be a bit difficult because we need some connection between this residual and the projection, right?
Yep.
In the first, like, and what exactly what is L for the residual, right?
Right.
This is what we don't.
Yeah.
We are thinking about understanding.
But they're not the same. All I'm saying is that both of them can converge to machine precision. They will not necessarily converge to the same thing.
Yeah, I tend to agree. We need to investigate. Like this is a very interesting mathematical question. How we can connect these. Yeah.
Okay. Thanks. Very nice presentation, by the way.
Thank you.
Is there any other question? Thank you, Adar, for your wonderful presentation.
Thank you.
And since there's no question, thanks everyone for attending this week's Chrome seminar. Everyone has a good weekend. See you next week.